Okay, video 5, we were talking about the fundamental theorem of calculus, where fun is the primary part. Fundamental theorem, okay? And you need this to do the question. Now, this may not seem to be what you need to answer the question, but it is, okay? And let me give you some examples of the fundamental theorem outside of this question. So let's do something really simple with, say, a polynomial. What if the thing you have inside here is x cubed? Well, what do you know if you want to take the derivative of something and get to x cubed? Well, it had to be x to the fourth, but the coefficient in front of it must have been a fourth, because you're going to take that exponent and multiply by the coefficient in front. But you also could have a plus c. So if you take the derivative, let me kind of write it this way. So what does that mean? Well, this plus c is going to be part of whatever the c is. You're going to get rid of it by subtracting itself from itself, right? So it's going to be, you're going to say something like 1/4 of b to the fourth plus c minus 1/4 a to the fourth plus c, and those c's are going to cancel out. So the constant of integration is not necessary when you're working out a definite integral. It's okay, but it just gets in the way. Okay, it doesn't help you because you're just going to subtract it anyway. So we usually just set it equal to 0 for simplicity's sake. And so then we just go ahead and answer the question. Okay, so as long as you have just something simple like a polynomial, then these antiderivatives are really, really easy to work out. And here, like I said, I just did this thing using letters just to make it more general, but you could literally take any polynomial and answer it now. So you could literally do little f of x is square root of x. It doesn't have to be just a straight up polynomial. Anything with the power rule, x to the minus 3 plus x to the fourth minus x to the 7th over pi, anything like that. And you could integrate it from anything to anything, 7 to 100, I don't care. Integrate it anywhere you like. So just using that really simplistic tool, you can do that. But the point of calculus is not only to get you to do calculations, because a computer can do that, right? But to get you to think about what it means at a deeper level. So now the question you're being asked asks you to use this in a deeper way. Okay, so what's going on here is the exercise is specifying what f prime is, which means what is f, little f, and it's claiming that in here we're going to put e to the t sine of t, and this is just a dummy variable, so if we used an x, whatever, we can use a t, it doesn't matter. Now we can make it a t. So it told us what little f was, but what it wants to know is it wants to know what capital F of 7 is, and you know that capital F of 2 equals 5. So that's the information you have. So the point is you have B and A to play with, and it doesn't really matter which one you do, but I will recommend that you put f of 7 here and you subtract off f of 2 because it just seems easier. And so then this is going to be the 7 and this is the 2. When you flip your order of integration, it just causes headaches for everybody. So this is the part we're looking for, and this part we know to be 5. Okay, so that's the clue. That's all the clues. And I will say you can feel free to use Wolfram Alpha or Desmos to help get you through some of this question, because that's a difficult integral. But I want you to sort of think about what's going on and piece together what you know. And again, go ahead and use technology to help you get through some of this and figure out what the answer to this question is. Oh, I will give you a little clue. Yeah, Desmos actually has a tool that will do the rectangles for you. So that's your clue. See if you can figure out how to get Desmos to do the annoying numerical stuff for you. It should bring up a beautiful picture for you, and you should be able to wield it pretty accurately. That's okay. computer assist is perfectly fine as long as you understand what it is that the computer is doing. If you don't want to use Desmos, that's fine. Let me just remind you how to use Python also. Okay, so this is how you would just get Python up and running. Again, you can use REPL.it, that website, or you can install Python, or if you're running on a Macintosh, you probably already have Python 3, which pretty much works the same way for most of these things. And then you can just evaluate f wherever you want. You could do something like v equals, and I'm just going to make something up. These are not the points you want to use in the exercise. But you could easily do something like this, like here are my t values, and make an empty vector for each element in the t vector, append to v, evaluate f at that element, and then you can look at it. You could sum them up. You could sum up some of them, you could divide by, whatever. So that's how you can make short work of those calculations in Python. Again, you can also do this using Desmos. Like I already alluded to in question 1, so if you forwarded to this point, if you're doing this question first, I'll just repeat that. If you have anything of this format, x to the p, and I'm just going to make some random number, okay, arbitrary number, I can take the antiderivative of this pretty easily because I already know that if I have this function and I need the derivative, it's going to be x to the n minus 1 all over, n x to the n minus 1. Okay, so I know that that's how I go forwards. So going backwards shouldn't be hard. I just have to sort of think through what I'm doing. And so if this guy is the derivative, right, what is the original function? If I had subtracted 1 to get here, then I must add 1 to get back. But now instead of multiplying in front, I have to divide in front, right? So like I have to double check to make sure this works. I always just double check to make sure this makes sense. If I multiply by 8.2, so 8.2 divided by 8.2 is going to give me 1. And I subtract 1 and I get back and I say, oh wait, there's one more missing piece. I could put anything else here I want, any constant. You can use k or c. If you are on WebWork, it will accept capital and lowercase c as well as k. Most of the time. Sometimes it's very picky, but it usually tells you if it's going to be picky. So if you want to just add in a constant of integration in WebWork, K and C are both acceptable choices for that variable name. Okay? Most textbooks use C, but K is also a very common choice. And so this is the technique you want to use for 2A, for question 2A on the worksheet. Okay, so for question 2b, what if you want to take an antiderivative of something of the format sine of nx or cosine of nx? So remember, again, if you're going forward, let's say forward, you're going to look like this. Okay, you take the derivative of sine, it's cosine times that 3. So what does it, when you're going from cosine back to sine, you have to divide by that. So if you have f prime is equal to cosine of 7x, let's say. Then you're going backwards. Well, the derivative of sine was cosine. But I must have multiplied by 7, so to go back, I must divide by 7. So you should constantly be thinking about what your rules were for taking derivatives and make sure that once you get to where you're going, you're going to be able to start with f, take the derivative, and get back to f prime, and like, aha, the constant matters. And then the same process happens with cosine. I'm going to let you figure that part out yourself. Okay, question 2c looks like it would be very easy to take the derivative, but very hard to take the integral, and that's intentional. But there's some trig rules you may have forgotten, which will get you out of this jam. Namely, that if you have sine of x squared, you can simplify that, or cosine of x squared. You actually know how to do this. And I'm going to show you how graphically and sort of explain what's going on here. So if you had just sine of x, let's try to remember what this thing looks like. 0 to 2 pi, sine of x would look something like this, right? And so sine of x squared, well, where sine was 1, it's still 1. Where sine is negative 1, it's 1 again, and 0 is still 0. But what ends up happening is you get a new sine or cosine curve that looks like this. It's a bad picture. Okay, maybe I can fix this a little bit. So this new function is right here. It averages at 1/2. So this function is equal to 1/2. And what is it now? It is actually going to be 1/2 plus 1/2 of the following, right? Because now the actual, you're recentering it on 1/2, but you've lifted it, and multiplied by -1. Let's see. So this would have been, it would have otherwise looked like cosine, right? 2 copies of cosine. So this here is what it would look like, a cosine, but it's twice as fast. So it would be like cosine of 2x, all right? So it's going to be minus cosine of 2x. Okay, so I think that's enough of a clue. So you can use the same process to rewrite cosine of x squared. Just draw it out, remember what it was, rely on your geometric intuition. I don't know about you, but I'll probably never for my whole life memorize this. I'll just always like sketch it out and try to remember what it was by looking at it. And that's what I expect you would do too. So I expect you go through that process and then you say, oh wait, now we know how to take the antiderivative of this piece, and now we're home free. Okay, so for question 3, you have a couple choices for how you're going to approach 3a anyway. You can just take this whole thing, multiply it out, and just do it brute force. You can just go ahead and do that. Multiply that out, and you'll get x cubed minus, I think, 6x, I don't know, like 6x squared, I don't know. Just keep working it all out, multiply it all out. And then you can just use the tools you already know. The other trick, though, is that you should realize that there's a symmetry in this problem that you can harness. Even though it's not an even or odd trick, you know that 1, 2, and 3 are the roots of this cubic. And you know it interlaces like this. And it says we want to know the area between the x-axis and the graph. So it's going to be, the integral itself will be 0, but because like if you went from 1 to 3, but it says the area. So you could just integrate from 1 to 2, and then this part is going to be double because it's asking for the area. So even though the integral would normally be negative, it's specifically an area question. So you have to make everything positive. So you just integrate once you figure that out from 1 to 2, f of x, you calculate that, and then times 2 to get your final answer. This question for 3b is just one you need to be patient. It's just got a lot of little pieces that you have to keep track of. But you want to remember what sine of 2x looks like. This is the part that will, once you unlock this piece, then it should be smooth sailing from there. Sine of 2x, let's see. Well, it's going to look like sine of x would look, but instead of going 0 to 2 pi, it will make a full cycle by the time it gets to pi. And so it will look kind of like this, right? But the integral they're asking for is 4 times sine of 2x, so you figure that out. But where does this thing go? It goes from 0, so it starts here, and it goes to pi over 3. So where is pi over 3? So I don't know, but if you split this into 3 pieces, this is roughly where it goes. You know this is going to happen before you get to the crossover point. So you know whatever it is, it's strictly positive. So if you're asking for an area, all you need to do is assure yourself that this entire this entire curve is above the x-axis. And once you've assured yourself of that, then you can go ahead and crunch the integral, and the integral will be the area. So the issue here is, the question is, does area equal to the integral? And in this case it is yes, because this is strictly positive. Then you can go ahead and just take the integral. And that's the big takeaway from that problem. Okay, the two little fun facts you need to do for A, you need to know, and you probably do know this, the derivative of e to the x is e to the x, so the integral of e to the x is e to the x. Don't forget your plus c or your plus k. But other than that, that's fine. And whatever number you have, you could have even pi if you want. It comes along for the ride just for free. Okay, so whatever you do. And the other little fun fact is, if you integrate a plus b dx, you're allowed to split this into a, capital A, and capital B. So the point is, you can split up on the plus and split up into two separate integrals. So go ahead and do your 3e to the x as one thing and your 2 sine of x as a separate thing, and then you just glom them together at the end. You don't need a plus c twice. Those two get combined and you just need one of them. Okay? So that's the trick there. Now this question, 4b. I'm just going to step you through the algebra a bit for this. X over x plus 1 over x is equal to 1 plus 1 over x. So it looks trickier than it is, but it's not that much different from the problems that's directly below it. So realize that 4b, maybe you should do 4c and then 4b, because they're really very similar. Okay, so the reason this one is a lot of fun is that if you try, okay, this will fail, but I want to show you what will happen if you do it by accident, okay? If you have a derivative that's x to the negative 1 and you try to use the power rule to undo it, like you say, okay, hold on a second. In order to get to negative 1, I had to subtract. It was 0 to begin with. That means I was like, whoops. So if you do this, if you ever go through these steps and end up with 1 over 0 times x to the 0, that's a problem, okay? So don't do that. So why does it seem like all of a sudden we need a different rule? Okay, so what do? We just say, oh, well, we know by memory, this is the natural log of x, and you can go ahead and finish the exercise. But I want to take a moment to explain what's actually going on from a calculus standpoint, because this thing is so beautiful and so lovely that it cannot go on without some kind of explanation. So let's say the following. If we have some power, all right, then f is usually equal to x to the p plus 1 over p plus 1 plus some constant, okay, some constant. But the limit as p goes to negative 1 of this guy, kind of, it looks like natural log of x, but there's a constant missing. So I'll show you what's going on. Okay, I'm starting with 8, and I'm going to work my way down and say, what do these things look like? I'm going to work my way down to negative 1. But I could try like putting a negative 3 here, and I put a negative 3 here. There's one example. Okay, what happens if I put like, I can't put a 1 in here, but I could put like negative 1.1. Well, I guess Desmos won't do that. So maybe I should try Wolfram. Okay, Wolfram doesn't have the problem that Desmos does. So what happens if we put some zeros in here? What happens to this graph? So you'll notice that these axes are getting wackier and wackier and wackier. And that constant of integration is going to actually take care of us. So let me try to fix that. Ah, that looks better. Now every single time I add another 0 inside here, all I have to do is I have to add another 0 here, and that's going to fix that constant of integration problem. And this thing is going to look more and more like the graph of natural log, like we expected it to. And so this is all just to show you that calculus is not in fact broken, and that the limit of these functions, they do go, let's see if I can get them to both plot together. There you go. Okay, so even if you let p be negative 1.0001, you can still use the power rule to take its antiderivative, and you are basically recreating the natural log curve. And you're not using anything other than the power rule. You're just carefully picking that constant of integration to make sure that the function evaluates to 0 at x equals 1, which is what we need to make sure that we're tracking the natural log curve. So we're just making use of that constant of integration strategically to make sure that we line up our shapes. Let me see if I can back up a little bit so you can see that they're not actually identical. And so you'll see, hopefully you'll see they're not identical. Maybe we should go further out before we can see the difference. I'm actually surprised that they line up that closely. Okay, you can see that they're slightly different now. So let me just go ahead and take away one more 0 and just let them come apart a little bit more so you can see this with your own eyes. There you go. Okay, so your natural log is the purple curve, and the curve we created using the power rule is the darker blue curve. Okay, so the power rule is actually alive and well under the hood, but the natural log curve is the limit of what the power rule tells us that curve should be. So they're all part of one big happy family. They actually do work together. And finally, I think what you need to know for question 4D is just trigonometry, reminders about trigonometry. I often have to just remind myself of all these things, so it's okay if you've forgotten them too. I'm always forgetting my trig, but the great thing about math is you don't have to actually remember anything. You just have to remember how to remember things, and then you don't have to remember anything at all. So let's say this is a theta. You're going to go like sine, cosine, tangent, cotangent, secant, cosecant of all these thetas. Okay, that's going to be y, x, and r. Sine is y over r. Cosine is x over r. Tan is sine over cosine. You get all your reciprocals. You should remember all these guys. And then if you want to pop in an angle there, you can put in like 45 degrees. 45 degrees is equal to what? Pi over 4, okay, which is what you need for exercise 4D. And so that makes this triangle half of a square. That means x is 1, y is 1, r is equal to the square root of 2, and then you have your sines, cosines, and tangents for all that. If pi is 30, as a funny reminder, 30 is pi over 6, 60 is pi over 3. They both have a 6 and a 3 in them, and 45 is the one in the middle. Kind of middle. I'm putting middle in quotes. Okay, so those are things to remember. Of course, if you remember that 360 is equal to 2 pi, you can figure all this out. But these things we use so frequently in calculus, you may as well just memorize those as 3 separate little facts. Like you remember natural log of 1 is 0, natural log of e is 1. Those are things that should always be on the tip of your tongue. Okay, so then what do you get? You should remember that sine and cosine are really the same thing. They're just shifted. So once you know what one piece is doing, all these pieces are doing the same thing, but there's essentially your 45 degrees is down here, your 30 and your 60 are here. So you really just have to remember these this sequence of 5 values, and then they just keep repeating. So the sequence of 5 values obviously starts at 0, and it goes to 1, and then we can fill in a chart. And here, for your amusement, is the world's dorkiest memory device to remind you of the sequence of these values. So obviously, the square root of 0 over 2 is 0, and square root of 4 over 2 is 1. Square root of 1 over 2 is just 1/2. This is obviously another way of writing 1 over square root of 2, and that helps you remember where the square root of 3 over 2 goes. It goes right here. And now you have a cheesy memory trick for all your sine values, and the cosine values just follow suit. And that is what I believe you need to know to successfully complete worksheet 5. Take care. See you soon.